sklearnutilsdiscovery. Description: the sklearnutilsdiscovery process aims to identify and leverage the most suitable utilities provided by the scikit-learn library for a given machine learning task. These utilities can range from data preprocessing techniques to model evaluation metrics, allowing for efficient and effective data analysis and model building. Inputs: dataset: the input dataset containing features and labels relevant to the machine learning task. Task: the specific machine learning task being addressed, such as classification, regression, clustering, or dimensionality reduction. Problem domain: understanding the specific context of the problem, including data characteristics, desired outcomes, and potential constraints. Outputs: selected utilities: a list of relevant sklearn utilities identified for the task, including data preprocessing techniques, model selection methods, evaluation metrics, and visualization tools. Optimized pipeline: a pipeline constructed using the selected utilities, tailored to the specific task and dataset. Steps: problem definition: clearly define the machine learning problem and its objectives, including the desired outcomes and performance metrics. Data exploration: perform exploratory data analysis to understand the dataset's characteristics, including data types, distributions, correlations, and potential outliers. Utility selection: identify and evaluate relevant sklearn utilities based on the task, data characteristics, and desired outcomes. This includes examining data preprocessing techniques, model selection methods, evaluation metrics, and visualization tools. Pipeline construction: combine the selected utilities into a pipeline, ensuring appropriate data flow and dependencies between steps. Hyperparameter tuning: optimize the pipeline's hyperparameters using techniques like grid search, random search, or Bayesian optimization to enhance model performance. Metrics: performance metrics: evaluate the model's performance using relevant metrics such as accuracy, precision, recall, F1 score, or mean squared error, depending on the task. Time complexity: assess the computational efficiency of the pipeline, considering the time required for training, prediction, and data processing. Interpretability: evaluate the model's interpretability, considering the ease of understanding the model's decisions and the ability to explain its predictions. Visualization plots: data distribution plots visualize the distribution of features and labels in the dataset, helping to identify potential patterns and outliers. Feature importance plots create visualizations that show the relative importance of different features in the model's predictions. Learning curves plot the model's performance against the training set size to assess overfitting and underfitting. Confusion matrices visualize the performance of classification models by showing the distribution of true and predicted labels. Fine-tune parameters: preprocessing parameters adjust parameters for data preprocessing techniques, such as scaling, normalization, or feature selection methods. Model hyperparameters optimize hyperparameters for the chosen machine learning model, such as the number of trees in a random forest or the regularization strength in a linear model. Pipeline structure: experiment with different pipeline structures, including the order of steps and the inclusion of additional utilities, to improve performance. Uncertainty methods: confidence intervals: calculate confidence intervals for model predictions to quantify the uncertainty associated with each prediction. Bayesian inference: use Bayesian methods to estimate the probability distribution of model parameters, providing a more nuanced understanding of uncertainty. Ensemble methods combine multiple models to reduce variance and improve prediction accuracy. Challenges and fixes: Challenge 1 Data imbalance. The dataset may contain an uneven distribution of classes, leading to biased model predictions. Sample use case that resulted in Challenge 1 A fraud detection dataset with a significantly smaller number of fraudulent transactions compared to legitimate transactions. Fixes to Challenge 1 employ techniques such as oversampling, undersampling, or using cost-sensitive learning algorithms to address data imbalance. Challenge 2 High dimensionality. The dataset may have a large number of features, making it computationally expensive and potentially leading to overfitting. Sample use case that resulted in Challenge 2 A text classification dataset with a vocabulary of millions of words. Fixes to Challenge 2 use dimensionality reduction techniques like principal component analysis, PCA, or feature selection methods to reduce the number of features. Challenge 3 Missing data. The dataset may have missing values, which can hinder model performance and require imputation. Sample use case that resulted in Challenge 3 A medical dataset with missing values for certain patient attributes. Fixes to Challenge 3 implement techniques such as mean imputation, median imputation, or more sophisticated methods like k-nearest neighbors KNN imputation to fill in missing data. Challenge 4 Choosing the right utility. Determining the optimal sklearn utility for a specific task can be challenging given the wide range of available options. Sample use case that resulted in Challenge 4 Choosing between different feature scaling techniques for a regression task. Fixes to Challenge 4 Thoroughly research and compare different utilities based on their strengths, weaknesses, and suitability to the specific task and data characteristics. Experiment with various options and evaluate their impact on model performance. Challenge 5 Hyperparameter tuning. Finding the optimal combination of hyperparameters can be time-consuming and computationally expensive. Sample use case that resulted in Challenge 5 Optimizing the number of trees and maximum depth in a random forest model. Fixes to Challenge 5 Utilize techniques such as grid search, random search, or Bayesian optimization to efficiently explore the hyperparameter space. Employ strategies like cross-validation to avoid overfitting during hyperparameter tuning.